All right, let's get started. So looks like we lost a few. Usually that's what happens. Everyone's worried about not having enough seats. But all right, so today we'll sort of get ready to do the first homework, which is due on Tuesday already. It's not much of a homework, but there's a lot of little pieces that we have to kind of get settled. So as I will be doing with many homeworks, we'll spend quite a bit of time in class kind of discussing the homework, both the solutions after the fact and lots of the template code and so on before. So the whole class is sort of driven by the homeworks, really. We have substantial homework assignments that help you kind of learn the stuff, and then I kind of try to guide you through it. One thing to note is that the homeworks, they're due generally at the beginning of class on Tuesdays. That might change, but it's always at the beginning of class. And there's no extensions generally, because we talk about the solution in class that day. If the whole class is having trouble, or there's a problem with the template or whatever, or I don't know, there was some other event that means we have to push things back a little bit, we have a little bit of room for pushing back, a couple of times throughout the semester. So we can't do it for every homework. We can't just delay, right? But there's a couple of weeks budgeted in there. So that's something we can sort of discuss either in class or in Piazza, like, okay, maybe we should use one of those weeks now. If we use, okay, so in order to get started with any homework, really, we go to the class page. And this year we're experimenting with GitHub Classroom. It's a little bit of a different setup, but I'm kind of getting used to it. But I think it'll work fine. So I'll just demonstrate a little bit how we use it. You probably haven't run into that before, or have you? Have you used GitHub Classroom? No, but GitHub, yeah. Many people have used GitHub naturally. So this is a little bit special. You get your own. Every student gets their own repository per homework. Right? So you get invited to do a homework, and then you get a repository. You check out that repository. You contribute some things to it, and then we grade your entire repository. In the past, we've done it with branches. So every student has their own private template, private repository, and we grade a particular branch. Now it's a repository of its own. There may be some inconsistencies in the homework descriptions, like throughout the semester. Let me know if you spot one. Put it on Piazza so people know that I've already been let know. And I'll fix that ASAP. All right, so let's take first a look at the class page. So you find the homeworks over here, number 1. And so here, what we're doing is really setting up your machine so that you can do the homeworks. And then we're doing a little bit of dealing with makefiles and things at the end. First thing you need to know is we're all using Ubuntu. We're all using the same version of Ubuntu. There's a good reason for that. We're using all sorts of different tools like GDB and Object Dump and GCC and so on. And if you have a different version, even a little bit, your binaries might look a little different, and you might not be able to see the same things that we see. So in order for all of this to work, really, we need to have a virtual machine. Or if you have a PC, or if you want to pervert your Mac, you can install just Linux straight up on it. If you can get Ubuntu to install whatever it is. We use the latest stable Ubuntu version is what you should be using. It doesn't say which one it is. Let's figure that out. All right, so you should have, if you were registered like as of the first day of class, you have already gotten a free license for VMware. I don't know if you got an email about it. If you just click on this one, you ought to be able to sign in and get this for you. Or get the license and download and so on. If you don't, let me know. I'll forward it to the support people that handle it, and you'll get your license. It's generally pretty quick. Yeah?
I had installed the VirtualBox on my computer, so is that okay?
I wouldn't recommend VirtualBox. I've used it in the past. It's been horrific, and VMware has been great, relatively speaking. What's that?
You convinced me.
Yeah, in particular, I think the performance was a real problem with VirtualBox. And it's not like we really care about performance, but for some things, it just gets weird. I'm not sure. Anyway, there's two pieces here. There's the build environment. In order to just create the operating system that we're actually using, XV6, we need to have a compiler and such. And that build environment we're using Linux for. You don't have to run the OS inside an emulator inside the emulator, right? But you can, and it's probably the easiest. So I'll show you how we can do it here. All right, so we set up the Linux environment. That should be pretty straightforward. Whatever is the latest stable Ubuntu version, they have all these various experimental things, but there's one that's called Stable Long-Term Support, LTS. Let's go with that one. All right, and then you have to install QEMU, and this is if you want to be running XV6 under Linux. So now we have QEMU, which is another emulator. It's running inside of VMware, which is an emulator, right? It's a bad idea performance-wise, but we really don't care about the performance in QEMU. Right? So that's up to you. I prefer to run it on my Mac. And so in that setting, it goes like this. All right, so that's not it. I have things set up in a kind of a peculiar way. It might be worthwhile to take a look. So we'll do that. Maybe you learn a thing or two along the way. All right, so I am running VMware. Where is it? Here. Right now I'm running 1604. If that's the latest LTS, you should use it, but otherwise not. All right, so I got the server version because I didn't want to bother with the whole desktop clicky experience. I have enough clicky on my Mac. So I just installed the Ubuntu server, and then I started running an SSH server on the virtual machine. After that, I can forget about this window, which is an annoying window. So now I can go SSH Linux, and I'm in my Linux machine. How did I get this SSH Linux to work? Anyone? Why does Linux work? etc host, exactly. Right. So in here I put the IP address and Linux, and that really helps with saving some time and remembering. Another very good thing for saving time, something I often do, is I put it like this. Here. So now I've said, okay, these host names, they all should point at my machine, which means I won't get shit. I won't get anything, right? Very good idea if you want to save some time, I found out. I would also suggest uninstalling, what's it called? I should remember this. This little game thing from the Seattle company, what's it called? Steam, that's it. Uninstalling Steam is excellent for succeeding in 385. All right, just some suggestions. I'll leave this alone for now. Okay, so that's one thing. Now it's easy for me to SSH in there. I can do all my work there. But of course, if I don't have a Linux desktop environment, I can't very well run a graphical QEMU emulator. Right? So I run that one on my local machine. But then I have a problem. I'm building things in Linux. How do I access the files from OS X? There's various ways to do it. One really cute way of sharing file systems is SSHFS. Highly recommended. Let me show you how it works. I'm using it at the moment. Let me see. Oh, come on. Aha, it's my Emacs. I'll just demonstrate with a different path name. Okay, so I go like this, sshfs, Linux, colon, this is a host name, colon, and then whatever directory. With just colon, it means the home directory on my Linux machine. And then I say, where do I want it to appear? In this testdir, I just created that folder, right? It should be empty, but in testdir is all the stuff in my Linux home directory. Really convenient, works with any SSH host. It's something that I use a lot. Okay, if I want to get rid of it, I go umount testdir. Okay, so later on in the course, we'll learn how to add the functionality for mounting some file system into a folder. What just happened here, we'll implement that for our operating system, but for now, let's just use it. Okay, so inside of my Linux folder, I then have, I think we should go in here. In this x86 public, I have the stuff. So now, in fact, why don't we back out a little bit? How do we get the sources? All right, here it is. So I've installed Git. I've installed, oh, that's over here. I've installed QEMU. I have all these tools. Now it's time to get going. All right, so in my Linux machine, I want to just delete this. And we'll go git clone that thing. All right, so the way this is set up is I have one central repository with the x86, and that will have any homework templates that we need for a particular homework. For this first homework, there isn't a template. We just use the master branch of this repository. So I checked out the repository. Who has not used Git before? Okay, very good. So we should be okay. We're not doing very advanced Git work here. It's basically check things out, commit your changes, and don't forget to push. Right? If you commit your changes to your local machine, it's just there. The homework hasn't been turned in yet. So you got to make sure you push it to the right, to your turn-in repository. And we'll see this in a little bit. Okay, so I check this out. I go x86 public, I say make. What's this? Ah, sorry. I tried to build it on my Mac. All right. My Mac build environment is not the same as my Linux build environment, so that didn't work very well. And we all need to have the same environment so we don't run into this problem. So I go SSH to Linux, do the same thing in there, and you noticed I was working in my Linux folder there. So this is actually the same folder that we were just working on. So if I say make now, that's a lot better. All right. So now I have two choices. If I'm using, if I'm doing this on the Linux desktop, I can run the emulator right away. And then I say make QEMU, and it should show up. In fact, I'm not running it on my desktop, but I think it shows up anyway. I have a cute X sharing interface. Okay, so it works just like that. You can set that up too if you want the extra headache. So here I actually started the program in Linux, but then this X window showed up on my OS X machine. Oops, sorry about that. Anyway, now this is here. This is not Linux anymore. Inside of here we're running. Ooh. Okay, so much for the X sharing. It doesn't know what my key codes mean. All right, anyway. So that's one way you can start it. That'll work fine. If you have a Linux desktop environment, you're just running it in there, it'll work just fine this way. And if you want to do it the Mac way, and you would have a Mac window, we go to the Linux directory. Something going on with some speaker here. Let's see if I can turn it off. And then I run QEMU, and here's a command line. You might want to maybe you want to look at it later on, in the recording, and then a window pops up looking like that. So same story. This is the x86 kernel running now. I can type my commands if I want. All right, let me close the door here. All right, so we have a working x86, right? And that's pretty much half the homework. Once you've installed the Linux and all of that. And then finally we have to do a little bit of work. I'm not going to do the work here, but I do want to show you how to push your homework up to this, what was it called now? GitHub Classroom. So you get something, you get an invite link. I have to update this a little bit, but let's see. Here's the invite link. This stuff is a little outdated. There's an invite link somewhere. I thought there was an invite link. Okay, there will be an invite link. Was I still editing it, maybe? Oh, there. Oh, there it is. Right. So I click the invite link, and then you select your email. We should go by your email here. If you don't have your email on here, let me know and I'll add you to it. Please don't start your own repository by skipping here. If you do so, we'll have the wrong identifier. It won't match up for your grades. It just get weird. So, but I'm gonna skip it because I don't actually have one of those IDs in there. I accept the assignment. What GitHub does now is they create a new repository that's called hw1 Jerickson. Jerickson is just my GitHub username. So that's the repo. And it's an empty repo. And there's a way to clone it. That's how you clone it, right? Just like any other repository, there isn't anything in it. Yeah, sorry about the font size. That's the clone URL, but it'll be like any other GitHub repository. Okay, so if I want to turn something in, I think this will be the best way. Okay, I didn't actually try this, but this will be good. So now I've already checked out the public repository, right, that has all of the template code in it. So I'm going to want to make a new branch. So now I'm in homework 1 branch, and this I'd make some change. Oh, there's something weird with my nano. I'll just use Emacs. So I was just going to add a new line to my make file. So I made a little change. I commit that. This is the easiest way to do it. -am, A for add all the files to this staging, like stage all these files for my commit. Everything that I've changed. Make a nice comment. Final commit for homework 1. Okay, so now, as long as I didn't add any new files, I'm done committing this to my local repository. If I added some new files, I actually have to say git add the new file, like that, right? And then that'll be tracked for later on. Next time you can say git commit -am. So am doesn't add all files, like build files and things don't get added there. It's just all files that were edited among the ones that previously have been added, like this. I'm kind of harping on this a little bit because it's so common to make mistakes with the turn-in when using Git. Git is great for many things, and it's good to practice it, but it does have a few peculiarities. All right, so then finally, Now, how do we turn this in? Because we checked it out from this public repository that you certainly don't have write access to. Right? But we want to push it into this other place, your homework repository. So to do that, you need to add another remote. Anyone worked with remotes before? Yeah, cool. So I can say, see which remote repositories are there right now. There's one, that's the public one that we were dealing with. That one has the name origin locally. So now I add another one. Let's call it homework 1, because there's one repository per homework, right? And I had that was my URL for it, so that should do it. Oh, git remote add, sorry. And now I should be able to say git push, and this might do just that. Let's see. So this says push, I hope, my local branch up to the homework 1 repository. But let's see. Yeah.
Just wondering if I wanted to you register in the repository and know I'm part of your classroom. Where is the link to do that?
Yes, it's on the homework description. Well, I clicked through here, so let's go back. Here. So in the under get the XV6 sources. Okay, it's not set up the homework template. I changed that. This is to get the homework template. This is to get the invitation. I will reword it a little bit to make it more sensible. Anyway, so you don't actually need this until a few steps later on when you want to turn something in. Okay, so let's try this. All right, that seems to have worked. So now I pushed up the entire XV6 repository into this homework 1 repository, right? That's just how it's gonna be. 4,900 commits. Oh well. What's a few bytes? Okay, so are we done? No, there's one more thing we had to do, because we always screw up when we're dealing with homework turn-in. So now the way to check it out is to git clone the same repository in a different folder somewhere else. Homework 1. Let's see what's in there. That looks good, and I think there should only be one branch. Homework 1, yeah. So if we do it this way, you get into the homework 1 branch for free. Usually it's like a master branch or something, but since there's only the one, I guess it did that for us. That's very nice. So now we can just say make, and then run it. You know, we make to make sure that actually it's working. It's compiling, sorry, then we run it to make sure it's doing what it's supposed to do, and then we're done. Right. Please always try cloning your repository this way, because it's so easy to make a little mistake. And now you spent hours getting this thing to work, and then finally you turn in the wrong stuff, and usually you don't get any credit for it. We do require it to be at this point in GitHub at the right time. Okay, questions on this? Pretty straightforward. Yeah, good. Okay. Let's see, was there anything else? Ah, yes. So now the rest of the homework is making a tiny little program. Right? It takes, it's a C program. It just takes 2 inputs and then outputs this. So you say divide 105, and then you get this output. That's it. That's not the challenging part. Probably you can figure out how to write that program in C at this point. What could be a little bit tricky is you don't have a printf that can print decimals anymore. There's no floating point support in the printf function, but there is a printf function, so that's nice. And then we're writing this program. We're writing it in Linux, right? But then it's supposed to run in x86, so we have to build it within the makefile context. Right? There's this big makefile. I'll show you what it all looks like. This thing is what builds x86. And it basically all a makefile does is a series of commands, right? Compile this, link these two things together, right? But when you're compiling it for a different OS than what you're running it on, you need all these special flags and stuff. So you could never hope to, say, take a Linux binary, copy it, if there was such a thing, copying it into x86 and then running it. It just isn't right. It relies on all sorts of system calls that we don't have, dynamic libraries that we don't have, and so on. So the only way to build it is through this makefile, and I'm not going to tell you how to change the makefile. Right? So that's part of the homework. Figure it out. And please don't discuss it too much on Piazza. Don't say exactly how. You could maybe be nice and offer a hint at some point. The whole point here is that you need to dig through this makefile, try to figure out how it works, right? At least part of it. Okay, so once you've added this, yes, let's see, right. So when we're running this thing, it looks like this. Oh. What is this little weird mute thing? I know, but does it have to keep saying it? Okay, unmute. That's great, and then it'll crackle instead, maybe. All right. Okay, so check this out. I'm telling QEMU here that we're going to run a 64. We need a 64-bit machine. There's all sorts of QEMU machines that can emulate. Fortunately, we figured it out. So the 64-bit version of x86 is working now. We'll be using sort of modern instruction set. I'm telling it I need 512 megs of RAM, pretend RAM, of course. And then I say there's two hard drives. This is just how x86 was set up. There's one, the x86 image, which has a boot sector, which we'll learn more about in a moment, and then the kernel right after it. The boot sector loads the kernel into memory and then jumps to the first instruction of the kernel. And then, once the kernel is sort of ready to go, there's a second image. This is the file system. The file system contains all of the files that you see when you run it. So when you're in here, and you're running x86, there's, what is that? 15 files. Right? These contents, and your program, this divide, will be one of these. Right? Just another binary. These files are part of the fs.img. So that's what's there's two things being created by the makefile, right? Two targets. One target is this xv6.img, the other target is fs.img, and you'll want your divide to be part of this fs.img. So that's a little hint for how to get started with that part of the homework. All right, so I wonder, maybe let's start talking a little bit about boot. Then. Like, how does a machine get started? So when you power on your machine, let me close this. Oh yeah, this is another thing. This QEMU is very power hungry. So, or maybe it's not QEMU's fault, maybe it's x86's fault. It's just running in a tight loop, trying to schedule some process, and there's never anything there. And it doesn't realize that it should go to sleep. So it tends to heat up your laptop quite a bit. Just turn it off when you're not using it, is what I'd suggest. Okay, so when you power on an old machine that doesn't have a battery and all that, right? Just power it on. What happens first? Like, how does this thing get going? What do you think? Any suggestions? Sorry? No, go ahead.
It boots it.
It boots.
Yeah.
Yeah, but what is boot? That's the question.
That's a better question.
Yeah. The boot process. And actually the next homework is going to be a boot sector. So we'll get intricately involved with boot. Oh, yeah.
I'm going to really mess up, but I think the BIOS knows to jump to a certain level.
Okay, very good. Okay, so we have a familiar term, perhaps, BIOS, the basic input-output system. Does anyone know what BIOS is? Like what it does? All right, but it doesn't start quite there. So the CPU, suddenly it has power. And then what's it supposed to do? How does it know what instruction to run? There are no instructions in memory, right? RAM was just cleared. Or at least it clears when you stop giving power to RAM, there's nothing in it. Right? So, yeah.
Does it load the first sector on the hard disk?
It doesn't. It doesn't know what a hard disk is. The CPU has instructions, normal assembly instructions. The best we could hope for is an out W, right, to write to a port. And if it knew which port the hard drive is listening to, would be good. Unfortunately, the CPU doesn't. Yeah.
The BIOS has read-only memory that is powered by a CMOS battery.
Okay, very good. So this BIOS, it sits in, it's not, yeah, so you say read-only memory. Read-only memory. In reality, it's flash. Okay, so it used to be ROM. It used to be you had to kind of order a new chip. If there's a bug, you order a new chip, you pop it out, you put the new one in, and your PC is working better. But now there's a little flash chip on the motherboard, or yeah, I would think it's on the motherboard and not inside of the actual CPU chip still. And it's hardwired into the RAM bus. So if you're trying to read from a certain address, if that address starts with a whole lot of zeros, right, and then a few other bits, then the flash memory chip responds. So the way the memory bus works, if you've taken 261, maybe you're slightly familiar with it, basically all these chips are just listening to the address bus, and they see, oh yeah, these are mine combination of ones and zeros, that means I should respond. And then it reads the rest of them to see which byte in its memory it should return on the data bus. So the same thing here, the flash memory is just a slow version of the same thing. So it just sees, okay, it's reading from my byte, let me output the byte on the data bus. That's the general idea. Okay, so ROM, or this flash memory here, is holding a bit of software. It could be something like a few hundred kilobytes. Okay, so we have software in memory. And now, how does the CPU know where it is? Where to jump? Any ideas how you could do it? What's that? Go to the first memory address, 0. And that's pretty good, although it's very common that someone would make a programming mistake and like jump to 0 because you have an null pointer or something like that. So putting it at 0 exactly maybe is not the best idea. But yes, it's hardwired. So it says, okay, I'm going to jump to this address, and I think it's something like something like that, I think. I don't quite remember. But we don't have to look into it right now. Anyway, it's a hardwired address somewhere that then jumps to wherever the actual BIOS code is. So that's the one thing that's really hardwired in the CPU. Where do I start? Right? And for the rest, we can update this BIOS software. Okay, so what does this BIOS do? It has a bunch, let's see, contains a number of useful subroutines. Let's call them subroutines. They're actually, in the BIOS terminology, they are interrupts. It's old stuff. right? This is, the PC is now probably, 40 years old, right? About. Or is it 50? No, 40. 40 years, about. So, and it started out having a BIOS. So the general idea is there's a BIOS, little subroutine for reading a character from the keyboard, for outputting a string, for changing the color of the text that it outputs, for changing the video mode, for doing beeping a little bit in the microphone, very basic things that as a programmer, as a normal program programmer, right, you wouldn't want to have to do this all the time. Read a sector from the disk. It's pretty complicated reading from a disk, so it's better if there's a standardized format, standardized way of accessing the disk no matter what kind of disk it is. This sounds a lot like an operating system, right? It's a really basic sort of operating system. There's no console. There's just a bunch of subroutines. There's no scheduler or protection or anything like that. So it's really just a little sort of a library of useful functions. Okay, so the first thing though that the BIOS does is it initializes the hardware. So what do I mean by that? Well, there's a lot of different things you might want to do to hardware when it starts up. You might want to tell the hard disk to start spinning. I don't know. You might want to set the video mode to something sensible. Right? Maybe the graphics card starts up in nothing. It doesn't show anything, and now you turn on the screen. Right? That sort of thing. Yeah?
So when you say that the BIOS has a bit of software on it, is the subroutines, is that what you're referring to as the software on it? Or
Well, it's, okay, so software is just, instructions back to back.
Yeah.
And so, yes, there's lots of instructions. Some of them start running on power on. It probably starts at this address, it jumps somewhere and just has a lot of instructions, things that it wants to do before it gives control over to whatever comes next,
Okay.
right? And then there's also a number of handy subroutines that programs later on can call to say, okay, now I want to read something from disk number 2, and then back comes the contents.
So
right?
subroutines are part of it, but it's not the entirety of it.
Exactly, right. Okay. Let's make it like this instead. Some hardware initialization code, and then there's some handy functions. Okay, so toward the end of all this initialization, there's something that you've probably encountered. Question is, like, this BIOS stuff, we don't even use it. Now, sometimes you use it. You hit delete, right? And then a little menu comes up, and you can control a thing or two. So that's BIOS. It's a relatively complex piece of software. It comes with the motherboard. Every motherboard is a little different, so every BIOS is a little different to accommodate this. But these subroutines all work exactly the same. It's a common interface for all of these PC motherboards. That makes it easy to kind of get started. But pretty soon, we'll want to just start ignoring this stuff. But it's hard to get going. So this is a good place to start. It actually runs in 16-bit mode. It's also called real mode on the x86. So normally now these days we run in either 32-bit mode or 64-bit mode. Right? 16-bit mode is just what the CPUs back in the day supported. That was the high tech, and the 8-bit was the low tech. Okay, so toward the end, BIOS starts wondering, now what? All right, it's initialized all these things, it's ready to run another program, but what's it going to run? The operating system. Which operating system?
As far as I know, the hardware consists like this particular area of the hardware on which the operating system's initialization is done.
Okay, we're in pretty good shape here. All right, so the BIOS needs to find, toward the end, BIOS needs to find out what to do next. You may have seen, when you hit delete, you may have seen you can change this disk ordering. And so you say, oh, first check on hd1, and then check the floppy drive, and then check the CD-ROM or the flash drive, right? What is it that is checking? Well, it's reading the first sector on a disk. A sector is a 512 byte chunk of bytes. All disks, pretty much ever, are divided in sectors. They're not physical, I mean, physically they're not anything. It's just that we index the contents on the disk in terms of sectors, 512 bytes at a time, or also called a block. So what the BIOS does is take a look at its internal list that the user has configured. Usually it says hard drive 1 first, right? Checks the first hard drive, reads the first sector on the first hard drive to see if it's a boot sector. If it's a boot sector, it loads it into memory and then jumps to that place in memory, and from there on the BIOS isn't involved anymore. So now the boot sector is running, right? How does it know if a sector is a boot sector?
I think like there's the last 2 bytes of some special sequence.
Yeah, exactly. So there's a hard-coded little sequence that's supposed to go at the very end of a boot sector. And if it's not there, you know that this is not runnable code. This is some other garbage. So I'm not going to try to run that. I'll check the next disk, right? See if that one has those 2 bytes in it. And then eventually you run out of things to try. And then it says, no operating system available. Right? Sometime, maybe you've run into that at some point too. And then the BIOS just stops there. That's it. Okay, but usually we find one. Actually, let's see. I think I have a boot sector here somewhere. Boot block. Okay, so here's a boot sector. We can see how big it is. 512 bytes. It's 512 bytes because sectors are 512 bytes. We can only have one. What the BIOS does is read the first sector, put it at, okay, read first sector, first drive. If it ends with, let's see what it was, 55AA. It could have been anything, right? But 00 would be a bad choice because there's a lot of zeros usually if it's empty. So if it ends with 55AA, then it's a boot sector. Aha. Isn't it like that? Yeah. Right. Okay, what? Anyone want to tell me what this is all about? Why did I write it like this? Sorry, what? Endianness, yes, right. So Intel is a little endian architecture. Little endian means not that we end with a little one, but we begin with a little end. We begin with the little end of the number. So here, the first part, the first thing that came is the little end, right? The lowest order digits in a 16-bit number. This is an 8-bit number. So in an 8-bit number, there's no ordering involved. It's just like that. And then when you put these two together into one 16-bit number, those are the little bits and those are the big bits. Right? So the little end comes first, which means you have to put those there. Okay. So endianness is going to mess with you, I think, during the semester at some point. Things start looking backward, you know. Might be why. That might be why. In fact, it's very likely to mess with you even in the third homework. Let's see. Okay, it only really isn't it has any impact when you start dealing with individual bytes versus larger words. Right? If you sometimes have large words and sometimes split them up into individual bytes and deal with them separately, then you probably end up with some endianness problem. Okay, so anyway, if it's a boot sector, then we load the sector the 512 bytes into memory at address 7C00 for no particular reason, right? This is another thing that was hard-coded way back when, and we can't really change it now. You know, we have 40 years of this history. You try to change it, it's probably not worth your effort. Okay, so, and then jump, and that's that. Now it's over for the OS, for the BIOS, because the BIOS doesn't run once you. This is an assembly instruction, right? So now we jump to this address. Now we're running those instructions. Whatever instructions were on the boot sector are now in memory. We can run them, and after that, the BIOS doesn't get involved. Of course, now it's up to the boot sector to do something. All right. What are we supposed to do? What's a boot sector usually for, do you think? I told you before. But you want to load the OS, exactly. We want to stick the whole OS kernel, at least, in memory. So once you have the kernel in memory, now you jump to the beginning of that. You know, you can't put the kernel in the boot sector. Why? Yeah, the kernel is going to be much bigger than 512 bytes. Even this this little Linux kernel is, no, sorry, not Linux, the little x86 kernel looks like it's 196,000 bytes. I think there's some debug symbols and things in there too. It's probably not quite that large. Oh, yeah, I do this all the time. Oh, there you go. Okay, so 75,000 bytes. Anyway, it doesn't fit in boot sector. So, now we need to read it from disk. Right? So the little boot sector needs to find the kernel on the disk, load it all into memory, and then jump to the first byte of the kernel. But how do we talk to the disk?
BIOS methods.
Exactly. The BIOS has some handy support for this. This is one good way of doing it. Let's take a look at how this works. We'll use our trusty Google for that. That should do it. int13h. So this is kind of arcane. I think it's useful to see sort of how things are set up. If you want to read from the disk, you use the instruction int. Right? That's interrupt. So these interrupt instructions, or all interrupts, what they make the machine do is stop everything it's doing right now, jump to a predefined location in memory. Usually, that is in the operating system, that's an interrupt handler that's dealing with whatever interrupt you triggered. In this case, the BIOS came before us. So the BIOS set it up already. It says, oh, if an int13 comes in, jump to this address. Right? There's a vector of 256 entries that says for each one of these numbers, says which address do we jump to. So for int13, the processor automatically indexes into the 14th element of this vector, sees the pointer, jumps to that address. Okay, so BIOS happens to have some useful instructions sitting over there. Unfortunately, there's only 256 of these ints, if that many. I'm not 100% sure about that. And so, look at that. It's the 20th entry because it's int hex. Sorry, int13 in hexadecimal. So that is 19 decimal, and we're off by 1 because we start at 0, so ends up with being the 20th entry. All right, so we jump to this bit of code, but still there is only probably 256 entries, and there's more than that many functions in BIOS. So if we want to be able to do more than that, we need to somehow multiplex over these numbers. This is This is very common. How does the BIOS do it? Well, it looks at what's in the register AH. Right. If in AH it says it's a 0, then we reset the disk drive, right? And so on. If it's a 1, then we get the status. All right. So now the boot sector wants to read something from this disk. What do? Well, we stick an appropriate value into AH, read sector from drive. Perhaps we put a 2 in there, right? We're going to have to put a few more values in, and we'll see in more detail at some other point. And then we get it to read multiple sectors. This one, yeah, it seems like it can take multiple sectors. Yeah, so here we say, this is actually not the one we're using. I think there's one called extended. This one's better. 42H. This is what everyone uses. So basically we tell it which drive, and then we tell, oh, and here are all their other parameters. So how many sectors do you want to read? Into what address in memory should the contents of these sectors go, and so on. And then we're good to go. Okay, so in the case of XV6, it's actually pretty simple, because now we have a boot sector, 512 bytes, and right after that we just paste in the entire kernel. The whole 70 kilobytes of kernel just goes in that xv6.img. That's what we're looking at. So, in fact, let's take a look at that. Okay, and we ought to see the AA55 here. So hexdump, you'll find, is probably a useful tool at some point. We'll look at lots of useful tools over time, but here's a good start. So here's our boot sector, just the raw bytes. There's no difference between data and instructions, right? They're just bytes. There's no way to tell the difference, but we know that, okay, it's going to end with a bunch of zeros, probably, if we didn't fill the whole thing up, and then AA55. That's the boot sector. And then comes something else. All right? And this is the beginning of the kernel. In fact, this is the ELF header. I wonder if that is supposed to look like ELF, even. It looks a little bit like it, but it should be a 3, right, if it's ELF. That's probably not it. Anyway, so this is the ELF header. ELF is a standard format for executable files. Let's see. Actually, it starts like that, 45.7f. Let's check the kernel, see if it's the same. See? So that's the boot sector's first 512 bytes, and then right after that comes the kernel. So now you can imagine that writing the boot sector is pretty simple. You just say, well, read the next sector and on, however long it was, and then we're pretty much done. It also turns out that a couple of these bytes specify the address we want to jump to. Let's take a look at that too. Read ELF tells us that sort of thing. ELF being the format, the executable and loadable format, 64-bit, right? If you read it out, so this is the magic, okay, right? The first few bytes have to look like this, then we know it's an ELF format. Okay, so that's good. 70F45, that's exactly what we saw. Later on in that thing, we get this, the entry point address. This is a header, right? It's encoded differently, but let's see if we can find it. FFF8 kernel. Here it is. Here you got the ordering again. Screwing with you. Start with the 8, right? And in fact, I think it gets even worse here because we have a long. I'm not sure. Anyway, so inside of the beginning of the header for this ELF file, it says, yeah, this is the first instruction you should be running. So we don't run the header, right? This is just some magic number. It's not instructions. So how do we know what to run? Well, the boot sector knows that the kernel is an ELF format. So it reads the entire kernel into memory, checks the right index in the header, and see, okay, this is the address I should be jumping to, and then we jump there. And then finally we're ready to go. Okay. So boot sector loads kernel into memory, jumps to entry point according to elf header. Okay, so what about if you're running Linux here? Does anyone know where the Linux kernel is?
Is it
Init.rd, no. Well, it's sitting in the file system, actually. So in Linux, let's check this out. So this is sort of the root folder of this Ubuntu Linux machine, right? You've probably seen this before. And right here is the kernel. So that's the one that needs to get loaded into memory. It's compressed. Usually it's called VM Linux. Let's see, maybe it's in, maybe there's another one in boot. No, they're all compressed. Okay. So you can't run it right now. First you have to decompress it. But before you can decompress it, you have to at least get this stuff into memory. Right? And that's sitting in some fancy file system. And file systems, as we will learn later on, spread data all over the disk. Blocks here, blocks there, lots of metadata and things. And so you can't just tell the BIOS to read this file, because files don't exist on disks. Right? Files are this idea created by a file system, part of the operating system, and the BIOS doesn't know that sort of thing. All the BIOS knows is read this block from disk number 5. And it's not just one block. We don't even know where the block is. Okay, so what we need in order to boot Linux, we need a boot sector that can understand the file system that's used here. I don't even know which file system it is. Let's see. This one, ext4, hideously complex file system. More lines of code than x86 for sure. Just the file system. Right? Probably 10 times as much code as x86. So how are we going to do this? We can't fit the file system code into the boot sector. And it's very handy to have the kernel sitting in the file system. Right? Because when you want to update the kernel, you just move a file around. This is what a user would want. So how do we get the kernel?
You could override the method provided by the BIOS.
Override the method provided by the BIOS, but where do you get the code from?
And that code, the basic code for ext, for reading ext, is where you jump to.
So we have nothing in memory except the BIOS that was already there. We don't get to change the BIOS in the flash, at least. Because if you start messing with that, you'll break your machine and everyone's unhappy. Right? So, so we have our 512 bytes so far in memory. And we need to read this hideously complex file system. And we don't have the kernel, right? Because it's somewhere else. It's hiding in the file system. We need a more complex bootloader, right? So what you end up doing is you have to load a second bootloader, one that knows file systems. So now you have your boot sector that loads a larger chunk that's sitting right after it. It's called a secondary bootloader. And that one can be any size you want, because you just tack it on after the boot sector. So it's usually the bootloader is going to be larger than x86. You have all this junk sitting there. Grub, you've heard about Grub probably. That's this. Grub knows a lot of file systems, right? It knows all sorts of cool stuff. It has its own little command shell. You can do all sorts of stuff with Grub. It's bigger than x86, and so that's what we load. And now we have access to all sorts of file systems. Now we can read what's on disk, load the kernel into memory, and then go and run that instead. So in a proper setup, you actually need these multiple steps. Why don't we just fix the BIOS instead? You know, the BIOS could just load the whole big boot sector, the whole big bootloader. Why go through this extra ridiculous 512 byte step?
Backwards compatibility.
Exactly. You know, you can take one of these, you can take an old disk sitting, like one of these floppy disks, sitting in your grandma's closet. Right? If you find a floppy drive somewhere, buy a USB reader, USB floppy reader. You know, you can probably boot it on your PC, not on your Mac, but on your PC you can probably boot it. That's pretty cool, and I think this is the greatest triumph both of Intel and the whole PC movement and Microsoft is the backward compatibility over 40 years is ridiculous. I mean, we can hardly manage it over months, right? You change a little thing here and there, suddenly it doesn't build anymore, or things are crashing. But yeah, it's very cool. I wrote a little silly bookkeeping program for my dad when I was 13 or something that he still uses in his business. And he's using it on a modern PC with modern whatever. It didn't change a thing. And Microsoft, they got that one right. It's very cool. Anyway, so we don't want to break backward compatibility when we can so easily just work around it. We just replace the little 512 bootloader with a little piece that loads a big bootloader, and now we're good to go. Same thing with the boot sector. It's running in 16-bit mode. The BIOS expects it to be 16-bit mode. We could have it go straight to 64-bit, but then you can run your grandma's floppy disk anymore, right? So we work around it. At some point, it's going to get a little silly, right? Thousands of years from now, you have all these layers, right? But yeah, we'll see. At some point, we'll probably change it. Okay. What's next? So we got it into memory. Let's take, in the last few minutes, let's take a look at XV6 then. Start looking at the code. So I am still cleaning up the 64-bit code. I didn't want to print it yet. And besides, I have to send it to the people that print it. But we'll look at the 64-bit code now, and you have access to it through the public repository. It'll change over the course of the semester. There will be more branches and things added in, and we'll clean things up. So every now and then you'll want to fetch the latest from the public repository. But either way, let's just see what's going on in XV6 specifically. Let's start with the boot block. Boot asm. So we're actually, for the next homework, we're writing a little boot block. So it's basically dealing with some other backward compatibility things. Right? There was some weird stuff going on. Where is it? It's not even on here anymore. Oh yeah, for a while there, back in 81 or something, they thought they were clever. Programmers thought they were clever, and they had some little workaround where you access memory above 1 megabyte and it wraps around to the beginning of memory again, and a lot of people used it for their programs. It's a clever little thing, and no one had any more than 1 megabyte anyway. But then some people figured, oh, we need more than 1 megabyte. Now there's no way to access it anymore, right? Because everyone's relying on memory wrapping around at 1 megabyte. So here's a little way to work around that, right? Because every PC started kept this wrapping around at 1 megabyte unless you do special handling to stop it from doing that, just so that every program still works. Backward compatibility. Okay, so anyway, we pretty quickly go from 16-bit mode, which we're running up here, to 32-bit mode. In the end, to get to 32-bit mode, we had to make a jump. And that's always like that when you change modes in an Intel machine. You always jump just to the next instruction. That's how it kind of happens. We're setting up all sorts of segments which we can ignore, and then very quickly, well, okay, this is good. Anyone know what ESP is?
Stack pointer.
The stack pointer, right. This is the 32-bit mode. The E stands for, I don't know, a 32-bit stack pointer. Without a stack, we can't run C programs. Right? Whenever you make a function call in C, we have this, we're growing the stack by a stack frame. Right? So now we know where the stack is. Okay, that's good. It's actually, I don't know where start is. Anyway, maybe somewhere. Can't see it. Oh, it's here. That's clever. Let's see. Yeah, okay. Actually, it seems like it'll overwrite the same thing. It's not going to stay very long. All right. So, and then we jump to this little bit of C program, and we're leaving the assembly, but we're still in the boot sector. So there's a C program that still fits in the boot sector. That's nice. Let's see what it looks like. Okay, so what are we talking about here? About 100 lines of code. This one doesn't actually use the BIOS. Turns out talking to the disk wasn't so complicated. So this program contains the code for telling the disk I want to read a block, and then also figuring out which address to jump to start running the kernel. So let's see. So we're reading in the beginning of the disk, the first 8 kilobytes, just to see what's there. And then for each of the segments of this ELF header, an ELF header consists of like, oh, this is an executable part, here's my static data, here's the stack should be in this part of memory, and so on. So this little thing just reads for every segment in the header. It says, okay, let me take these sectors from the ELF file, put them where instructed in memory. And I'll put these here. I'll clear that bit of memory here. I'll put that string over there. Right? Just prepare the memory layout to run the program. And then finally, we find over here, this is the header. This is the ELF header, right? In fact, if we go up a little bit, we can probably see the definition of it. Oh, that's the multi-boot header. Where's our ELF header? Oh, wait a minute. Header is a multi-boot header. Okay. Yeah, I merged the latest changes from the MIT version, and I think they stopped using the ELF format. Anyway, so in this multi-boot header, same idea, but here's the entry address. Okay, so we got your entry address. Oh, they made it all a little simpler by ignoring the ELF part. There isn't much of layout for the kernel. It's just, here's the stuff. Just load all of this in, and then we're good to go. So we're basically finding the entry header, casting it as a pointer because it used to be just an integer. This casting doesn't do anything. You know that most casting in C, at least casting any pointer whatsoever in C, doesn't change the value. This value is the same as that value. Because pointers are pointers no matter what. They're always pointing at the same place in memory. So why do we bother with casting it in the first place? And why do we care about changing the type?
For the compiler.
For the compiler, right. Usually the compiler is on our side. And so the compiler tells us, no, you may not jump to an integer. Right? Here we're trying to call an integer. If we hadn't casted this thing, we're trying to call this entry address. It's just an integer. Or was it an integer? Let's take another look up there. Yeah, it's a uint64. One cannot call uint64s, says the C compiler. So now it will give us an error, which is nice, because now we know we made a mistake. Or maybe we didn't make a mistake, we just forgot to tell the compiler, oh, no. this entry address here is a function pointer, right? This is the syntax for a function pointer that returns void, doesn't have a return value, and it doesn't take any parameters. All right, so now that we know that it's a function pointer, the C compiler will allow us to call it. Now what do you think this produces in assembly then? It's a call to a function that doesn't take any parameters and doesn't return any values. It's not a jump, actually. It would have worked. In this case, it would have worked because we never come back from it. It's a call. All right. So what's the difference between a jump and a call?
Return, you can return back.
Right. So how do we know? How can we? So there's a return, right? That's the difference between a jump and a call. A jump is like a go-to, and a call is like a function call. So how do we know where to go back? On a return, in the end, we go back to where we called from, but how?
It's in the program counter.
It's on the stack.
Stored in the program counter, the next address.
The program counter has the current address.
It's in the stack. You store the return address on the stack.
Exactly. So call takes the program counter value plus the size of the current instruction and sticks that onto the stack, decrements the stack value because the stack grows downward. So it decrements the stack value and then jumps to the address. Before we wrap up, let's disassemble this thing. And we're going to be doing a lot of disassembling. Oh, what is it? It won't let me do this, I think. Sorry. Hello. Right. Disassemble boot block, but it doesn't like that. I need to say something about the format. Something binary. Format. Where is it? Does it type? Come on. I want to get this. Okay, let us rely on Google. Minus B binary. Okay, let's try this again. Oh, and then architecture. Is that then? Architecture, there it is. Maybe like that. Come on. All right, let's try this too. Maybe it's even in here if we're lucky. No. Minus M I386. Okay, that should do it. I386. Oh, come on. Oh, that's disappointing. Well, I think there's it's a cheat here. All right. So here it is. I believe that's the end of it. No, it's not. That's boot main. Oh yeah. Okay, so that's the final call. Anyway, I will do better on the disassembly front next time. So for now, get started on the homework. I will update the turn-in instructions slightly. It'll be exactly what we did in class, but I'll update so it reflects that. it should be pretty straightforward, but you have to do it, because otherwise we can't do homework too. All right, have a good weekend, and I'll see you on Tuesday.